Hey everybody, thanks for coming out to PyData DC's August event. We'll be going over Dask distributed compute system. We'll be having Julia, head of open source for Saturn Cloud, run this presentation. Just before we kick off, I want to remind everyone that for these PyData events, we welcome people of all experience levels and want to foster an inclusive environment. So that being said, I want to go ahead and thank our sponsors, PyData, MetroStar, Spell, Capital One, NVIDIA, and NumFocus. From there, if you want to stick around afterwards, we'll be having a virtual happy hour. If not, we'll look forward to seeing you at our next meetup as well. If you're interested in doing one of these demonstrations for the PyData meetups, feel free to send a message to Hussein Sultan, and he's got his email here. If you have any questions, feel free to reach out to me on chat for that. Without further ado, I'm going to go ahead and pass this off to Julia.
Okay, thanks. I'm Julia. I am a Dask maintainer, and I'm the head of open source at Saturn Cloud. Saturn Cloud is a platform that runs in AWS and provides easy access to Dask and Jupyter on CPU and GPU instances. So now we'll get into Dask. So this presentation is really targeting like a little bit of a deeper understanding of how Dask works, and then also kind of giving some insight into how you can customize Dask to do exactly what you need. You can find these materials on my GitHub. It's called Inside Dask. I'll drop, maybe someone can drop this link in the chat actually, so I don't multitask. It's all Jupyter notebooks, so you can run it on Binder. Or just follow along. So to start with, if you've ever encountered Dask before, you've likely seen examples that use Dask data frame and Dask array. Those are high-level interfaces to Dask. So they mimic pandas and NumPy, and what they actually do so the interface is similar to pandas and NumPy. And what they do behind the scenes is they construct task graphs. So there's all these different ways of interfacing with Dask, all these collections, and then they construct task graphs, and then those task graphs just hang out until you are ready to call compute, and then they get sent to the scheduler, and the cluster takes over doing the actual computation. But Dask, the promise of Dask is that it will take care of most of that. So what all you really are supposed to have to think about is the high-level stuff, the array interface, and what actually happens with your what you're actually doing with your data, rather than what is going on behind the scenes with the cluster. So if you've ever seen Dask examples before, you've probably seen things like this. This is a NumPy. This is Dask array, which is the NumPy-like API. So you can import it, you can do random.random. This is the same exact method that's on NumPy. And what you get back is an array. And you can do array computations on that. So for example, you can do sum. And you'll notice that what you get back from sum isn't a real value. It's just this other array, another Dask array. And nothing actually happens until you call .compute. Similarly, you can do more complex computations, like adding a transpose, and doing a sum along a particular axis, taking the mean. And again, it just sets up this task graph, and nothing happens until you call compute. Dask data frame is sort of the same deal, but for pandas APIs. So this is just a demo time series data set, and you can do group bys on it, call that sum, and you don't, nothing actually happens, so you call compute. It's getting redundant, right? And then you can do basically most things that you can do in pandas. You can also do in Dask with the data frame APIs. So a lot of times people hang out at this level and they're happy, and that's great. But sometimes you need to like get in a little deeper to get the customization that you need to do your work. So what Dask data frames actually are they're little tiny pandas data frames that are all concatenated together. So those are called partitions. Similarly, Dask arrays are little tiny NumPy arrays that are all in a little in a pattern that represents the whole data set. So let's take a look at that. So this is our Dask array. We see the representation that we saw in the last notebook. And there's 8 different little chunks or blocks here. And they each have the shape of 250 by 500, and together they nestle together to make this complete Dask array. So we can look at a particular block. So we can just look at this 0, 1 block, and that represents just one tiny little piece of the array. And when you call a function, Dask applies that function to each block. So we can look at what that looks like. So here's our 8 different little chunks. There's a sum happening on each different chunk, and then those sums are summed together, those sums are summed together until you get the result. So every operation in Dask, whether it's a data frame or array or delete, creates some tasks. So in the example before, like each block, what creates each block is a task. And then also like the sum is a task, and there keep being more tasks that are joined together. And each task knows about its dependencies, and by combining all that information, we end up with a graph of all the requirements to get to a particular outcome. So that's really like the main thing that Dask is doing is constructing that graph. And that graph, it's a DAG, so it's a directed acyclic graph. So it only goes one direction, and there's no little loops that can spin out of control. So these are examples of some different graphs that work particularly well on Dask. Embarrassingly parallel is every task directly every task is just like follows its own path. So there's no dependencies on other parts of the data set, and you end up like a lot of times this is a transformation of some kind. And then MapReduce is like you're aggregating in. So that was the example we just saw with the sum, where you start with a data set and then you just keep aggregating. And the benefits of this architecture are that you never have to have all the data up front. So no single computer has to read all the data, which can help if you physically can't read all the data onto a computer if you have really large data sets. And also it can make things faster by taking advantage of like the multi-cores that computers have, and running things in parallel. So here is our same little example, but this time we're looking at .dask, which is the task graph. So in this case, it's a high-level graph. So we see that we just have one layer. So the only layer we have is random sample. So another way of looking at that is using visualize. And that's, you have like all these different little chunks that are doing random sample. I know you can't read that, but now you can. And then once you string together your whole computation, so the array is itself a task graph, and then once you string together your computation, you add in these other layers. So you see the transpose happening in the second layer, you see the add, and then the sum, and then the aggregation, and then the mean. And so you kind of steps through those layers. And for a visual representation, each like horizontal here represents one of those layers. So we can zoom in a little, but it gets kind of crazy. So this is the first layer at the bottom, the random sample, and then the transpose, add, the sum, blah, blah, blah. So once the graph is constructed, it goes through optimization, scheduling, and execution. So once we have that graph that represents the whole computation, nothing has been computed yet, but it goes through these stages. So this is a representation of the graph after it's been optimized, which involves like squishing together tasks that are similar and cutting out tasks that aren't necessary. And this image shows how it shows the order in which these tasks are going to be executed. So it starts at this dark red 0 and goes through like from red to orange to white to blue, all the way to this dark blue. And this is the order in which Dask is going to execute this, so that it always knows, it always has the dependencies calculated by the time it has to do the next step. So that's kind of how Dask works. So I wanted to show how you can directly access the blocks of an array. So we saw how you can call .sum on an array to get the sum. And that's the easiest way to do that and the best way to do that. But if you have something a little more complicated that doesn't always fit within the constraints of the API, of the array API. So here's an example where we are iterating over the blocks and applying a function to each block. So here's our array, and then we have for each block, we're going to compute the sum, and then we're going to be adding it like iteratively to that result. So let's see what that graph looks like. So this long graph that has you can see that it still has these 8 random sample blobs, and then they each go to a sum, and then they're aggregated, add. So it's kind of the same type of graph that we've been looking at, but it's now like totally custom in terms of the operations that you're doing on that. For another example, for data frame, we can have that same time series data, and we can do a group by on each partition of the data frame. So we'll do a group by, we'll do a sum, and then we'll sum up all that whole iterable. So this one takes a little longer to visualize because it makes a kind of crazy graph. But essentially, it ends up like every computation goes together with the next one, and the next one, the next one, the next one. And if you turn on the optimized graph before you visualize, you can see that what actually ends up happening is all these computations get calculated and they all get added together at the end. So the graph that you start with isn't, that's just to say the graph that you start with isn't necessarily the graph that you end up with if you're optimizing, which is you are by default. So after I saw that first graph, I was like, let me see if I can make a better graph. So this is an example where instead of summing onto the same result and like just building up the data, instead it does a tree reduce, so it sums with the nearest neighbor, and then like does that again and again. So you'll see that this graph is a little more reasonable, and it has this nice pattern of like joining together the results from every 2 partitions join together and then together and together, and it steps out that way. But it optimizes the same as the original. So the optimizations are pretty good, and you don't always have to be fancy. It's kind of the moral of that story. So far I've been talking about arrays and data frames. Those are very data-centric concepts. If you don't have arrays or data frames, instead of having blocks where the function is applied to each block, you can decorate functions with this delayed decorator and have the functions themselves be lazy. So we'll take a look at this. I'm going to generate a fake data set and store it on disk. It's just taking the time series data and putting some temperature, some fake temperature. That's just so it's easier off later on. So I have a delayed version here. I have a non-delayed version here. Let me make these more the same size. So this version just has it does this like sort of fake data processing pipeline where it reads in a file, it does a transformation on that data, it does the transformation on the data, and then it writes it back out to a new directory. And we're going to do that for every file in our data directory that we just generated. This version over here is the same exact functions, but now with this Dask delayed decorator. And so instead of the functions happening as soon as I call them in this like for loop, they're gonna just build up a task graph, and then nothing will happen until I call compute. So the only difference between these two is that I have Dask delayed above all these function definitions, and then I have Dask compute here at the end. So let me run these. So I'm just gonna run this one. I'm gonna run this one. And you can see that the Dask one already finished, and the non-parallelized version just finished later. So the point of that is just to show that these like embarrassingly parallel tasks it's really easy to get parallelism out of Dask with these kinds of tasks. There's other tools you can use to do this for sure, but it's very easy with Dask. So you can, in addition to using delayed on functions, you can also use it on objects. So you can pass, because a delayed can really wrap anything. It can wrap a callable, but it can also wrap just any old object. So all the Dask collections, the arrays, data frames, bags, they all have this toDelayed method. And what it outputs is an array with the same shape as every block essentially is converted into a delayed object. So now you can use those like blocks. So you can call like .sum on one of them, same as you can call .sum on one of the blocks. You get the same output, like good. But they don't have any sense of what they represent. So since Dask delayed can wrap anything, it doesn't know anything about what it's representing internally. It's a black box. So you can set up task graphs like this of adding A to a delayed object, and that's not an actual thing. And the Dask array has these guardrails built in where it'll trigger these errors and warnings and try to catch you before you while you're setting up the graph rather than the error happening on compute. So this one's I wasn't sure whether to include this. So sometimes the task graphs that Dask constructs are suboptimal. So if you're aggregating data and then use that data in the next operation, the data, Dask wants to hold that data in memory, and that's not always what you want Dask to do, because sometimes you need to free up that memory, or your workers are dying. So there's this kind of advanced technique where you can do graph manipulation to actually like change how the graph is constructed before you do any computation. So this example is reading in that data from that we generated, taking the mean of the temperature and then subtracting the mean and doing a resample. And you'll see that this graph, this task graph, there are these, that each little piece of data is both being aggregated to the mean, and it's being held around and then used again when that subtraction happens. So there's all these little vertical lines linking up the data chunks from below to the computation later on. And so instead of keeping that data in memory, the task graph can be restructured so that it goes all the way through the mean temperature before it starts on the and then drops that data before it starts on the subtraction step. So here we're just telling Dask to bind the temperature to the mean temperature. So that means that here I can show you what that looks like. The temperature. So before it gets a temperature, it has to go all the way through the mean step. So, and then what the output looks like is just joining those two things. So it goes all the way through the mean step and then gets the temperature again, and then it does whatever it needs to do after that. So an alternative way of achieving this behavior would be to call compute before you, another approach would be to call compute before you, before passing the mean temperature in, so that you just have an evaluated value. But sometimes it's important. Sometimes you want to keep the whole computation fully lazy until you're done. So this allows you to do that. The last piece I have to talk to you about is distributed clusters. So far we've been looking at Dask's high-level interface and the task graph. And now we'll talk a little bit about how the task graphs get executed. So there's a couple different pieces. There's the client, and then there's the cluster. The client submits tasks to be executed, and the cluster does everything else. So it schedules it, assigns it to workers. The workers do the work. So we can create a cluster. This creates a local cluster. There's all sorts of other clusters for any type of remote architecture. This client, what it outputs is this rich display that has actually a lot of information in it. You can keep drilling down and get information about all the different workers. You can get links to all their diagnostic dashboards. You can see their state. There's a lot of information in here, and this changed really recently, so it's pretty cool. We're excited about it. You can also, if you have Jupyter Lab, you can get the Jupyter Lab extension, and you can pull up plots right in line in Jupyter. There's a lot to choose from, but task stream is generally nice. I'll put it over here so it's not in our way. So when you call computations, like this one we just did, they run through the the cluster is the one that actually processes them, so you can see computations going through. So some things that I found that are handy when working with remote clusters is you can run things directly on the workers using client.run. So here I have my 4 workers, and I can run list directory on either just plain, or I can pass arguments in, and that'll run on each and every worker and output the results. That's really helpful so this bypasses the schedule entirely. It just allows you to interact directly with the workers, which can be helpful, especially if you're in a weird place and you don't know what's going on anymore. There's also this concept of worker plugins, which do something on the worker every time the worker state changes. So this worker plugin does a copy file, So every time the goal is to copy a file from your local client to all the workers. So you initialize it with a file path, and then it reads in that file path, stores it, and then anytime a worker comes up, it writes that data out to a file on the worker. So we can see what that looks like. This will not work for anyone but me, this last part, because I'm copying a file that's like up outside of this directory. But I can copy this cat picture to my workers. You can see it showed up here because it's slightly goofy because these are local workers, but in a distributed scenario, these would be workers on different machines, and passing data back and forth can actually become like kind of annoying. So this is a way that you can do that every time. And these worker plugins run every time a worker starts, even workers that don't exist right now. So if I scale down my cluster to 0, then I have no workers. Just checking that that's the case. So yeah, no workers. And then if I scale back up to 4, that same plugin will run on each worker. So if I do client.run lister, then they each have this they have this file uploaded to them. So that's really the goal of this talk, is to show well, basically most people will spend a lot of their time interacting with Dask in this Dask array, Dask data frame delayed way. But when that doesn't work for you, there's other options available to make Dask more customizable. So yeah, that's it. I can take questions. There's one question here in the chat that I guess I should have responded to at the time, but about the fancy graph. Let me share again. So it was the question is about this graph, and it's saying, why are there start and end numbers? So the way that this works is, first we construct a list of all the a group by on all the partitions. So that's the function applied to each chunk. And then while there's more than one item in that list, we take, if it's an even number, we're just going to sum everything by its neighbor. If it's, maybe the question isn't about this actually. Do you want to unmute and ask your question? Okay, they said it's in the multicolored graph. Let's see. So this one. Okay, yeah. So why are the start and end numbers 0? This is actually not a 0. This is a brackets. I don't know why it's a brackets, but I think that maybe is what you're talking about. But also the numbers are for each level. So the numbers in the square here represent the order in which they're going to happen within this layer. Actually, I do know what the brackets represent now. They represent the shape. or the location within the array rather. So the brackets here at the end mean it has no shape because it's just a value.
I think it's just maybe a tuple.
Yeah, but the tuple represents the location in the array.
Can I ask a follow-on question?
Totally.
Okay, so, I get that this is a directed graph and color coding is letting me see threads that go through here. But, when you originally gave the example here, the maroon color with the 0, you articulated that that was the start point of the entire process. But, so first of all, the symbology of the directed graph is kind of confusing me. What is a circle? What is a rectangle? We've kind of gotten over some of the numerology here. But why is that 0 not replicated in the layer below it if the numbers here represent the order inside the layer that the process is happening?
Because it's not well aligned by layer. So this 0 actually belongs down here, but it has no, it's kind of got a shrunken section because it doesn't have this like, the way that like the tree aggregation works, like not everyone gets joined in every layer. Some people just get passed along. So I think that that's what's going on here, where the 0 actually belongs down in this lowest level, but it's kind of gotten collapsed up. And I agree that that is not intuitive.
Julia, is there another form of this graph, like a, I don't know, like a broken down version where you can see some of the individual nodes and decisions that get made?
I'm not entirely sure. There's this version, which is the typical version, which shows like every, I can answer the circles versus squares thing too. The circles are functions and the squares are outputs. So the functions have their tasks and outputs, I should say. So the circles have these names like random sample, and then the squares have shapes, or I keep saying shapes, but it's a tuple that represents where in the structure that particular chunk goes. So it's the block location, I should say. So this is like the first block, and this is like the next one over. There's ongoing discussion about how to represent these things better and differently. There's also this representation, which I don't think I went into much, but this is like the layer by layer. It goes through what's going to come out of it. But I don't know if there's that much more about the ordering and how that gets decided.
This was awesome. Thank you so much. So I didn't know about the worker plugin. I've been doing the client.upload_file. So I guess the difference between those two would be that the worker plugin actually lives through worker restarts, or?
Yeah, the upload file has been rewritten actually to use worker plugin.
Okay.
This is just a little demo one that I made to show that you can do anything with worker plugins, basically. Like you can do, this is, upload file is like fancier. It's specifically for Python modules, and it like puts it in your path and makes sure everything's good there. This is just for like moving a file, and that's it.
Got it, but that was more of an example.
Mm-hmm.
I should not switch to this.
No, unless you want to do something silly, like sort of more basic like this.
Right, understood. Awesome, thank you.
Yeah.
I had a question about when you were talking about bind.
Mm-hmm.
I was just curious, like I'm probably too confused to ask like more of a meaningful question, but I was interested in what bind was doing and whether or not something was or wasn't in memory.
Yeah,
Yeah.
I can try to get into that. I don't know. So my understanding of the graph manipulation stuff is definitely limited, but my understanding is that what it's doing is, in terms of memory, is it's first going entirely through the mean step, so the aggregation step, and then it drops all that memory that's loaded in from the data files, and then it reloads in, it rereads in the CSVs to when it gets to the next step.
But
If that makes-
is it housing the output of the mean in memory still? Like, does that like
Yeah.
it went through the means? Okay, cool.
Yeah.
Cool. I think that makes sense to me. Like, cool.
Yeah. Yeah, that has, I mean, it has to
Yeah.
store it somewhere. Yeah, so it must be storing it in memory, which is why it's good for cases where you're aggregating intensely and then also using the original data, because it's not good for cases where you're not doing that and it's still a massive thing.
So then you can clear out some of the memory in your workers for more meaningful things, or if you're like kind of over encumbered in terms of resources, you could find results to particular steps. That's cool.
Yeah, I encourage you to look at the documentation about this. It's good, and there's a couple other methods that I didn't get into in this, but there's some other ways you can really get into it and mess with your graph.
Super cool. Thank you.
Yeah.
I almost want to harass you about some of those other methods. Can you hear me now?
Yeah, I hear you.
Yeah.
Yeah, you're just a little quiet, but I got you.
Oh, sweet deal. All right. So one of the methods that I found useful is Dask persist, especially because with Rapid, I work on the Rapids project. When we do run compute, it returns a QDF data frame instead of a Dask data frame. But if you run persist, it continues. I almost had a question. I have a couple of questions on it, but one of them is more on the memory management and the ability to use it as like a checkpoint in case like you want to do hyperparameter optimization, or is there a way to better manage the memory? Like you have this great graph, but I don't really I won't know if it's going to fail until after I run it.
Yeah, this graph manipulation work actually came out of that space. Like that's historically what people have done to is called persist, which loads the data into memory asynchronously, so you don't have to wait for it to finish, and it keeps it as a Dask array. But then it makes everything else like way faster once you've persisted that data, because the data's already there. So that's how people do it. If you have if that works, like if it fits into memory, then persist it. It's gonna be way better. If it doesn't, then there's other techniques that you have to use. So that's the history of where this bind stuff came from. It's actually, I think, exactly this example of normalizing climatology data and stuff.
So you're saying if I have a large data source and I'm reading it in, and it takes however long it takes to read in, I can use bind instead or along with persist to make sure that I read once, but I can handle multiple different sorts of operations, and then return back to the original persisted Dask data frame after I read, so I don't have to read every time I want to try something?
No, this is the opposite of that. This is if your read is quick, but you can't store your data in memory for a long time.
Okay.
So this is the read happens every time. Once you'll see the read CSV happens down here, these stay with CSV. And then it happens again up higher up in the graph.
So Julia, as an extension to that, I'm curious, are there sort of meta optimizers? Oh, sorry, Torian, are you still going?
If my internet's screwing up, then that's
good.
on me.
What was your follow-on, man?
I'm on VPN. Don't worry. I just wanted to. Okay. I was trying to understand, like, with persist, is there a solid way of like reading once and then allowing us to keep that that persisted data in an area of memory or whatever, and then just keep on working through our workflows and then coming back to that original persisted data and then working again from that workflow along a different workflow without even if I run Dask compute later on.
Yeah, I mean, I think that's what Dask persist does. Like, it keeps the data in memory. And you have to assign it. I didn't understand this at first about Dask persist. This is probably obvious to everyone, but you have to assign it to something. Persist. So people often do this, and that stores it in memory. So then, like, everything you do after that is very, very fast.
Right.
But yeah, I don't. Even if you call compute, like, it'll still be stored in memory unless it gets like, unless you delete the variable, I think, and then it'll get garbage collected. That's my understanding. But it sounds like we might be in a slightly different, a more different situation. Let's say.
Nope, it makes sense.
So Jeff, I know you had a question, but are you okay if I ask a question?
Go to George, because you're so polite.
Thank you. So I was really curious. I liked the when you were showing adding a string to something that wasn't a string, and it was basically saying, "Hey, don't do this." Is there like if you have like, is there something that exists? And I'm just in Dask because I'm just now starting to use Dask. I have a background in like typically it was like PySpark and pandas and stuff.
Yeah.
But if you have that graph set up, is there something that would maybe take like make the smallest possible like a single row partition for each of the subtests and try to check that what you're trying to do is not insane before you go ahead and unleash the beast?
Yeah, that's exactly right. That's what Dask does. So there's this private attribute called meta. It's there for arrays and it's also there for data frames, and I don't know about that. But what it is it's a, for arrays, it's a NumPy, like, so NumPy, 2Py array that is empty, contains nothing, but has the right D type and the right shape. And so that's what when I call array, let's even go back a step. If I call array plus a without the blocks thing, I get this error. What's actually causing that error is when the graph is constructed, Dask does a little tiny piece of work where it tries to do this operation on the meta, and it doesn't work, and that's what causes the error.
That's awesome. Thank you.
Yeah.
Yeah, well, I guess I'll go real fast, which was just, you've been showing us a number of the like optimization tweaks around sort of how to help it better, create a solvable solution that's actually efficient for whatever environment you're in. I'm curious if Dask has any partner projects or components internally for sort of that meta optimization. Like if you have a long flow program that you're looking to sort of quickly translate to Dask, but you realize that it probably needs quite a bit of I don't know, call it optimization for Dask, where like you were doing the binds to pull together similar functions that ideally need to be in the same worker nodes to produce efficient output.
Yeah.
Is there something that sort of can work with an existing program to understand like how to quickly turn it into an optimizable Dask parallel program?
Not that I know of. The optimizations in Dask are that you can write your own custom optimizations for Dask for whatever type of object you have. And then there's built-in optimizations for the top level collections of data frame array and whatnot. But I don't know of like an external project that does optimization. Actually, there is one that has to do with like caching that I know of, but I can't remember what it's called. I'll look it up and post back in the meetup if I can find it. So yeah, not that I know of, but yeah, I'll leave it there, I guess.
Fair. And as a follow-up, you were showing, and I know it was a bit of a toy example, but around sort of the bind function and sort of calling two separate aggregators, right? And that you had two separate aggregation functions or summary functions that were dealing with the same, that the way that they expected the data to be presented was the same, and therefore having them on the same worker nodes would be important. Is there some sort of programmatic, almost like, design pattern that if you use Dask will understand these are all aggregators or summary functions or things that expect data to be striped or structured the same way such that it will automatically optimize? And you were just sort of showing a toy example where if you don't have that, use this.
Yeah, there isn't right now. So there is a little bit, recently there was some work that went in that's actually, I think, going to be hugely impactful, which is to look in Dask always only looked backwards at its dependencies. And now it looks forward like one, I think. And that, and then it co-assigns work to the same worker based on the future as well as the like past, which I think has had really big impacts on performance. I'm trying to think. I think I have some slides about that. I can probably rustle up. Let me see. But so there is a little bit of that baked in, but there's also this concept of task annotations where you can assign the priority and assign which worker things go to. So you can really get in there and like do it. Like you can get in there and mess with basically everything if you want it to go to a specific worker or something. Or if you want, or you can restrict workers based on whatever, based on like some that have GPU and some that don't, or whatever constraints you may have.
Thank you. That was very interesting.
Mm-hmm. I'm trying to find that slide. I think it'll be cool.
I just want to say thanks, and that was super informative. I've been getting into using Dask myself, so getting to see a little bit more of a like fine-tuned demo is super helpful. So thanks for doing the talk.
Yeah.
Yeah, these were that exposed me to a few things I hadn't even played with. This is really nice. I love that you have these notebooks.
Yeah.
Thank you so much. This is amazing.
Yeah. I'll put the link to this issue in case people are interested in the chat.
Julia, I may have missed it joining a couple minutes late, but these notebooks that you've created, are they somewhere on the web?
Yes, I'll drop that link as well.
Perfect, thank you. And yeah, this looks like your personal work, so thank you for adding that to the community. This is really, really good stuff.
Yeah, it's heavily based off this tutorial that James Verbo and I gave at PyCon and Dask Distributed Summit. That was like, those are 3 and 4 hours respectively. So it's different, but if you want a more in-depth version of this type of stuff, there's also, I put a link to the recording of one of the recordings into to those notebooks as well.
Awesome. Thank you.